started again here. A couple of administrivia, and then we will get on with our last speaker of the afternoon. Here's the map to the restaurant. It'll be starting at 6 o'clock tonight at Wilton Manor. If you just come out of Barrows Auditorium and go west, which is that way, I think, and then go north when you get to Main Street. It's pretty simple. It's a pretty big intersection. It'll say Main Street. Go north. It's about 2 miles, intersection of Main and Geneva. And don't get too scared if this road says Schmally.
There's an H in there.
Well, so what? And unlike Chuck and Rich, I say kilometer. And I also say elevator too, but just in case, just a couple of other announcements. If you would please fill out the evaluation form. I'm more concerned about some comments that you have. Now, I know there's been some registration problems, there's been some administration problems. I ask that you just cut us some slack, because we know about just about all of these. What I really want to know is, how is this material to your grade level? And then if you guys are in education, what would you like to see if we were to do this again? That's really important, because I know it's above some of your heads. It's this is something I just want to know, what can we do to help prepare you for this type of material in the future? For those of you who are way in over your heads, on the last page of Chuck's analysis, there is a little picture that you could draw. That my student aide, Jeff Mila here, has done a good job with the coloring. Chuck, you're using a 386-33 over here. And we did a little zoom in on the URL, and it says, if I can read this, weather.com. I wasn't sure. So, actually, if you want to color that at some point and get to the guy with the long hair in the front, Alan Rosenberg, who put this on the Gilbert Zone, is going to be doing a contest, and he and Chuck are going to be grading them, and then we're going to scan them and post them, and so, whoever wins, wins. Also, one thing about the evaluation sheet, 1 is good, 3 is bad. Or 1 is really, really good, 3 is, okay, pretty good. So 4 and 5 are really bad, and don't put that down there. Is there anything else? Do we have any problems with tickets or anything else that we need to take care of now? Again, we'll have about an hour between here and the restaurant. And they'll be, for the first half an hour, they'll be just kind of sitting around. I think they'll have some, there'll be a cash bar. No open bars. And that's all we need. And then 6:30 dinner will be served. After dinner we'll have some announcements and some talks, and then we'll have the feature presentation about Vortex, and that'll kind of culminate this event. Tomorrow, 8 o'clock, is when the advanced spotter training will go on, and tomorrow will be more of a visual understanding of severe weather, and there'll be some of the guys here will be speaking again. Some other things from the Weather Service will be presented as well, and you'll get a chance to see how multi-county here in Chicago does its severe weather program, which I think is pretty exciting. Is there anything else that we need to take care of before? Yes?
When are you going to put that weather dress up that you're going to keep for the stuff that happened here?
I will email it again over Weather Talk and all the news groups that I can. As soon as we are able to get that, and hopefully that will be within a month or so. I talked to Gilbert and all the speakers, and we're going to try to make the videotapes available for the cost of the tape and selling as well, so that will also be announced in the next couple of weeks. At least that's our intent. Okay. Yeah, if you just check the COD weather site, there'll be announcements on that, and I'll just give you that in case you don't know what it is. It's pretty simple. Just do that one. Yeah, COD, it's College DuPage. Anything else that we need to do? Okay, our last speaker, despite the fact that he's a Dallas Cowboys fan, I don't know if that's a good thing or a bad, but he's a pretty good guy anyway. Roger kind of crosses the field in meteorology. Started out at the National Hurricane Center, and he's now worked his way up to the Storms Prediction Center, and he is the owner of an infamous storm chase vehicle called the Meat Wagon. And Roger is just, again, one of these type of people who just live and eat and breathe severe weather, and the passion for understanding severe weather is really apparent in all the things that he does. And what is the name of your talk? It was something with sludge in it, and I guess I'll just let Roger Edwards explain that. Roger?
Okay, let me make sure this thing's working here. Pitfalls of severe storms forecasting, model biases, bad analyses, and other forms of prognostic sludge. And the purpose of my talk here today is not to tell y'all all the intricate details of model resolution, model biases, things like that. You can look that up for yourself. There are some internet resources I put on a handout that Paul put in each of your packets that deal with that. And there are also some excellent resources on analysis, which comes before looking at the models, obviously. Those are in your packet as well, including a couple of essays by Chuck back there that are directly relevant to this. By the way, I'm going to use this picture to take great issue with Rich's contention that the only storms that are worth a crap are those that produce tornadoes. I happen to disagree. This storm did not produce a tornado, and it's the most beautiful supercell I've ever seen. Was my most enjoyable chase ever. Atmospheric violence does not have to necessarily involve tornadoes.
Probably a failure case.
But as Rich just pointed out to me, it is a failure case because I was there. The first thing I'm going to address now, Chuck and Al and Rich, they've given some excellent presentations on how to analyze. I'm going to try to show you a little bit on that, but also how not to analyze. And you know, you can hammer derived fields to death. You can talk about CAPE, lifted indices. You can talk about storm relative environmental flow. You can talk about helicity. You can talk about Bolt, Richards, and shear. But if you don't know how to draw an isotherm on the right side of the data, none of that means crap. You have to know, you have to start with the basics, and you have to be able to analyze maps. It's as simple as that. I'm going to start off with, of course, the impeccable analysis type. You know, those prepared by Storm Prediction Center. Now, actually, we screw up, you know, analyses probably just as much as anybody. It's just that you don't see it. But I'm going to show you some, kind of run you through kind of a typical morning at the Storm Prediction Center, as long as there's not a lot of active severe weather going on in various parts of the country, and we're not too distracted by that. We are going to do what Chuck mentioned as a throwback to his days at Sells. We still do that. Hand analyses of the full suite of mandatory level upper air maps, as well as surface maps. All the forecast desks participate: the mesoscale, the lead, the outlook, the winter weather. We're analyzing upper air and surface maps. We're working as a team. We're trying to get all of our ideas into this. I'll start with a 250 millibar analysis. It's kind of hard to see the data probably in this plot. Actually, it's not as hard as I thought it would be. A typical analysis, actually it's mine, so it may not be completely typical, but in this case we're analyzing ice attacks at 250 millibars. We're looking for maxima in the wind flow at those levels, for relationships between, for example, ageostrophic circulations and vertical motion in the atmosphere. And In this particular case, it's a fairly recent event actually, February 25th. Remember, we're looking at 12Z maps here. And we analyzed 250 millibars, isotachs, streamlines, areas of diffluence, not necessarily divergence, but diffluence. Let me run through this set of analyses pretty quick. 500 millibar analysis, it looks like somebody barfed on this map, but there actually is some method to the madness here. 500 millibar heights, also areas of coldest air at 500 millibars, thermal troughs, thermal minima in this case. There was an area of strongest cold air over northern New Mexico, actually south and southwest of this low. Obviously lows, highs, ridges, troughs at 500 millibars, even calls where we can find some. And height changes at 500 millibars. For example, if we have strong falls and not much in the way of rises, we would expect this thing to deepen some more, which is what it did till it lifted out. And going down through the atmosphere, again, we're thinking in 4 dimensions here because we're going down through the atmosphere as we analyze. We've also looked at previous maps. We're looking at satellite data. We know what's happened. We've gotten a good briefing, I hope. We know what's happened since the last 2, 3, 4 days it's evolved to this. So we have kind of a picture of what's been going on, and we can analyze what's happening now. Typical 700 millibar analysis, 700 millibar moisture, dew points greater than or equal to 0. That's not an absolute threshold, just a general guideline. If we can find areas of significant moistening that are below 0 that may have an impact on severe weather, we'll draw them. 700 millibar height, 700 millibar isotherms. There's an area of drying that doesn't necessarily meet the so-called threshold, but I drew it on the map anyway. And cold, warm areas at that level. Typical 850 millibar analysis. Let me get this thing straightened out a little bit. Areas of high dew points, fronts, if they're on there. Isotherms, obviously. Hard to draw fronts without knowing what the temperature fields look like. Matter of fact, I would contend that it's impossible. And obviously the lows, the troughs, important features, and the moisture at 850 millibars. And sometimes we'll draw things on these maps like isotachs, other features that are non-standard analytical features but may be relevant to a particular case, what I like to call situational relevance. You don't want to get stuck in analytic dogma and analyze the same thing every time, or else you're just a robot. 925 millibars. This is kind of loose criteria. We analyze different things at different times on this. This is a very changeable mandatory level. It's just off the surface in most places. It's under the surface out here, so I didn't analyze anything. I can analyze the temperature a few thousand feet below ground level, but it wouldn't do much good. And we're looking for areas of moistening, warm, moist air. We can also draw fronts. We can draw isotachs. We can try to look at the low-level jet. I personally like to look at sounding data more for trying to find vertical continuity among things, obviously, because that's what sounding is good for. This is not all the upper air analyses we do. There are some derived fields based on morning data. Now, on this particular day, there were not a lot of things to draw, but I wanted to keep it the same day. Surface-based LI, Cape convective inhibition, LI and Cape and convective inhibition based on a 100 millibar deep mixed layer near the surface. And we can analyze that stuff. Got other derived analyses besides this last one that I'm going to show here. Mandatory level, it's called mandatory level stability chart, but this is actually useful for some of the heavy rain forecasting work we're going to be getting into. Precipitable water, some of the older indices that are starting to fall out of favor, like sweat, K-index, are still on there. 7 to 5 delta T's, you can look at the soundings and actually get the lapse rate, so that's analyzed inconsistently. But what these kind of maps do is they do give you just a plainer feel for what's going on in the atmosphere. You can look at soundings till your face turns blue, but it kind of helps to have the data on the map and actually draw for it. Here is I want to go through an SPC meso-analysis. I'm going to start with the pressure, analyze lows. I like to draw lows wherever it looks like there's low pressure, even though there may not necessarily be a cyclonic circulation center there. If the data seems reasonable, the low gets put there. In this case, there was a binary feature. It had good continuity in time. It had actually an isalobaric couplet with it, as you'll see later. Here's a case where the dry line was really well defined in the isodrosothermal field, and troughs. I usually start out with these, drawing the pressure and the moisture fields, and any number of things can overlay on top of that. Obviously, once you put that in, you can draw fronts. I'm going to try to get these maps to match up here. Okay. So you start to see that the map is trending towards spaghetti here, but it's also becoming more useful because we're seeing patterns in the temperature, in the dew point, in fronts, things that can become relevant to the forecast. Let's toss some more features on there. Let's just analyze the hell out of this thing. And I like to do this when I'm at work. I'm like Chuck in one respect, hopefully not in too many, but I'm like, in one respect, I love to analyze. I mean, if I have time to, before I'm drawing a forecast, I'll analyze upper air levels and analyze all kinds of stuff on the surface. I'm not even sure necessarily if what I'm analyzing is relevant or not, but it's kind of hard to tell till I've actually drawn it in a lot of cases. And now we've got isalobaric analyses, 3-hour pressure rises and falls of a millibar or greater. Every millibar, actually minus 30 is minus 3.0 millibars, for example, right there. Drawing some streamlines on the map in yellow. That might help me find some areas of confluence in the winds, even if they don't necessarily correspond to what we've got drawn here, like say this dry line. Well, there's an area of confluence out ahead of that dry line. That might be important later, especially if we run some programs to see if there's actually convergence going on in there. They can help us find other boundaries. Obviously, if there are outflow boundaries, any convective features, such as the one Chuck did in his exercise or some of the others, put those on there as well because they're of tremendous importance in forecasting severe storms. Now, you can go a lot of places with surface analyses. That's just kind of an overview of how we analyze maps. There's a lot of flexibility in there, but those are the basics, and that's where we start. Now here's a case. I'll start into some pitfalls of analysis here. Here's a case where you have a strong isodrosothermal gradient in here, and it starts back in here. Now where do you draw the dry line? That's what I want to know. Somebody tell me, okay, that's 37, 43 is the dew point, 45, let's see, 30. I kind of rubbed that out when I analyzed that, but that's around 27 or so. 24, 51, 46, 47, 56, 57. Where do you put the dry line? Hey, somebody said a wind shift. Well, what's the definition of a dry line? Does it have anything to do with kinematic fields? I would suggest that a dry line has to do with moisture, not wind. Same way with fronts. A lot of times dry lines have pretty pronounced wind shifts on them. Other times not. Sometimes the wind's the same direction on both sides of the dry line. A lot of times it ends up that way when I'm out chasing and no storms form. In this case, there is a fairly pronounced wind shift there. There's also a wind shift there. And in here, do I draw that for a dry line? No. Any suggestions as to where I should draw this dry line? Where with respect to that gradient? Whoops. Well, let's see, west of Amarillo. Well, okay. Amarillo's gone down to 38 degrees. Pampa is still up around 40. Now, actually, I would tend to agree. Now, Steve Weiss up at Sells likes to say if you give 100 meteorologists surface analysis, they'll do it 100 different ways. I personally tend to agree with that suggestion, right on the eastern edge of the strongest gradient. Now, some suggestion, some analytic manuals or rituals say that you should analyze on the 50-degree isodrosotherm. Well, obviously that ain't going to work here, because what's the dry line going to do? Well, the dry line's going to arc up through Kansas and then back down across northeastern Kansas, northeastern Oklahoma, and it's probably going to, dry line's going to end up somewhere over the Gulf and over North Florida that day. Well, no, that ain't going to work. You're not looking for some absolute dogmatic number set in stone. You're actually looking for what you're trying to analyze. What's the definition of a dry line? Well, you're looking for a strong gradient in the dew point. It's like analyzing fronts. You're looking for a thermal gradient. You're not looking, wind shifts can help you locate fronts if you've got very limited data. Satellite pictures of cloud lines might be able to help you locate fronts out over the ocean, or at least insinuate where they are. But ultimately, if you want to find a front, you want to look for temperature. If you want to find a dry line, you want to look for moisture. So don't try to get too fancy when you're analyzing maps and analyze for everything under the sun when you're trying to analyze for the definition of the feature. And dry line has to do with moisture, so analyze it based on the moisture, not on the winds, not on the temperatures. They might be able to help, but if you've got a nice dense amount of moisture data there, you don't need anything else. It's about moisture. And that's one of the pitfalls of analysis, is trying to overanalyze and trying to complicate something more than it is. To avoid bad analyses, just use solid basic technique. A lot of the techniques that you learn in your synoptic lab classes, I hope, are not outdated. They're good solid analysis techniques. Analyze the lines on the right side of the data, look for bad data. As Chuck mentioned, is it bad data? You might have to go in quite a bit of effort to examine it and find out for sure. But follow recognized conventions, complete labeling. How do you know where the 50-degree isodrosotherm is if you don't label the stupid thing? You go back 10 minutes later and look at it, well, blah, 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 blah. Just label it. Save yourself some time. Smooth contouring of the good data. I mean, if your analysis looks like you're having seizures while you're trying to write, then you're not going to accomplish much, and you may even inadvertently introduce bad data. Isoplests fit all the good data. Again, analyzing good data is a difficult problem. But once you're fairly confident you've got a stack of good data there, make the isoplests fit. If you've got, for example, this map right here, don't draw the 46-degree isotherm east of the 47-degree dew point here if you think that it's good. Now, you would be, that seems really simple, but you would be surprised how many people I've seen, even at the Storm Prediction Center, violate that. And it happens all over the place. Okay, the lines are where they should be. There are reasonable geostrophic approximations for latitude and winds in the high levels, except in extreme cases of ageostrophy. But for the most part, if you have, for example, at 250 millibars, if you've got a nice fetch of what you consider to be good RAOB data, and you're drawing your height lines 70 or 80 degrees off of that, then either there are massive thermonuclear explosions going on through the atmosphere, or something, or you're just not analyzing right. Think in 4 dimensions, and of course, obviously, you're looking at the 4th dimension there being time. Compare with other levels. If you're not sure if data is reasonable at 700 millibars, you're looking at 500, you're looking at 400, you're looking at 250. You look at the soundings, you see if the soundings make sense. Look at the history of it. Okay, you're still not sure if this station is off. Well, did it look like it was off at 0Z if you're doing a 12Z map? If there's a similar problem at 12Z and 0Z before that and 12Z before that, and you're looking at your stack of radar maps on the wall, and all the ways you drill a hole mentally back through these maps, this station is off by 60 meters, then okay, chances are you got some bad data there. Even if your previous analyst did a lousy job, good continuity from previous data is a good idea. And whenever you're looking at a map analysis, don't trust it. Look at the data behind it, because somebody might have drawn the 46-degree isotherm east of the 47-degree dew point, for example. Look at the analysis to get the big picture. Examine the data underneath that analysis to see if it makes some sense. Now, some other tips here. Know the terrain and its influences from the surface through the mid-levels. If you're wondering why in the world you're getting this very high mean sea level pressure somewhere up in the Rockies, you think it's bad data. Maybe it is. Maybe it's not. Maybe this particular station, if you reduce it to sea level, it's way up there in altitude, it's cold. If you reduce that pressure to sea level, it might be 1,030 millibars, and all the stations around it are 1022. It might be legitimate. Know the terrain and how it influences the surface data, or whatever data you're looking at, even up through 700 or 500 millibars sometimes, at various times of the day and season, and under various ambient flow regimes. Obviously, you would not expect a strong sea breeze condition down in South Florida when a cold front is just swept through, and it's in the middle of January, and temperatures are in the 40s, and the winds from the northwest at 30 knots, for example. And other times, it varies depending on what the ambient conditions are. It's know the larger scale, know its influence on the scale you're analyzing. So you have to know, and those are terrain influences too. Sea breezes, coastal fronts, which we see quite a bit of, and lee side, areas of lee side subsidence, dry lines. You have to know how that works into the data. Use non-plotted data sources such as soundings. Again, like I said before, you can check that. If an upper air plot seems bad, before you actually draw for it, question it. Look at the soundings. See if it seems reasonable. For example, there's an anomalous dry pocket at 850 millibars. Okay, you have an 850 millibar analysis. And you're drawing all these isodrosothermal contours around this thing in your mind before you're actually drawing them in pencil, and you're thinking, something's wrong with this. But then you look at the sounding, and okay, the soundings to the east, the west, the south, the north of there, there's this layer of dry air that's just above 850 millibars. So the 850 millibar level slices through the moist layer, and then at this station it's just a little bit below. Well, there's really nothing wrong with that. It just happens to be you're using a level that's not representing the actual moisture field. So sometimes such data can be reasonable. Have excellent satellite imagery interpretation skills. Now this is useful in a lot of ways, especially out over the ocean when you're trying to analyze data where there might be a buoy every 400 or 1,000 kilometers, or never, as in the case if you're looking across the Atlantic. Had to deal with that a lot at the Hurricane Center. There was no way to know exactly where a front was. There might have been a ship somewhere off of Barbados. Maybe when he went through the front a day and a half before, we knew where it was then, but he's way down here off Barbados. There's another one off the Cape Verdes. But there's this, we know that a big cyclone is swept off the Atlantic coast, and satellite imagery interpretation can at least say, okay, within some margin of error, 50, 60, 100 kilometers, this is probably where the front is. Sometimes that's the best you can do. For severe storms forecasting, you can usually do a little bit better than that, but there are areas where it could be a problem, such as out west, for example, hard to analyze fronts around the mountains, and in data sparse regions. You can use radar data to help you in your analyses. It can help you locate outflow boundaries. Let's say, for example, that it's about 2 o'clock in the afternoon or 3 o'clock in the afternoon, and I'm just coming in and I want to see what's going on. And I'm told that there's some convection moved across northeast Illinois the night before. I look at the surface data, and there's some subtle wind shifts in there, but it's really hard to pick up. The temperatures are not that much different on both sides of the outflow boundary. I mean, over maybe 100 or 200 miles I can see a difference. But so, oh, what the heck, let's see if I can find this thing somewhere else. And I call up the Central Illinois ILX 88D data, and wow, there's this nice fine line right about where I think the boundary should be, but I don't know for sure. But in the radar data and the velocity data, there it is. Clara mode velocity, there's a line there. That kind of thing can help. You can look back at radar loops and determine where convection went, where the boundaries, guess where the boundary should have been laid out, compare it with your surface data. It helps refine your picture of the atmosphere a little bit better. You can plot non-standard but trustworthy data. For example, mesonet data. And VAD winds, profiler winds, if you're looking at upper level analyses. We started to automate that at SPC, plotting VAD and profiler data at the mandatory RAOB levels on the RAOB maps to help fill in the gaps. Now, obviously where the data doesn't exist, there's not a lot you can do with it, but it does come in handy and it is useful. If you have a data source that you trust, use it. Don't let it sit fallow, use it. It might help you identify something that you wouldn't have identified without it. This is last, and I put it last on purpose, but on occasion it can help. You can go back, you can verify model forecasts with current data, which actually you should do anyway if you're using the models, but for the purpose of surface analysis, every once in a while I find that once I've done my surface analysis and now I'm looking at model data, I look at an initial analysis, or I'm looking at last night's 0Z model run, for example, I think, wait a minute, there's a feature in here, does it exist? And I go back and look at my surface and I'm like, what do you know? It's there, I didn't analyze for it, but this thing actually shows up. It's not very common, but it can happen. So use multiple sources of data when you're doing your surface analyses that are not necessarily surface data, and your analysis will be a little bit better, and maybe you'll pick something up that you didn't have there before. But ultimately what's important is the basics, proper analysis technique. Okay, I'll talk about bad data. Look at that map long and hard and tell me what's wrong with it. Somebody raise your hand and tell me what is wrong with that map. Okay. Good, that's one. Obviously that is out of place. The terrain around there is hilly, but not ridiculously so. The mountains are off over here. There's really no reason for 1018.9 to be there, and especially given the ambient weather setting that we had at the time. What else is wrong with this?
That dew point sounds.
Oh yeah. As a matter of fact, a couple of stations in Kentucky are notorious for that. And if you've analyzed maps over a period of time and you've seen these things show up, you know, okay, their particular humidity sensor starts going haywire whenever the dew point gets above freezing, and it tends to stick around freezing. Well, you can account for that. And things like that pressure and that dew point, if you analyze strictly for the data, you'll come up, you're basically doing nothing more than a blind objective analysis, and you might as well just plot it up on your Mercatus or whatever, because you're going to get the same result. You're going to save yourself about 20 or 30 minutes, and you're going to get an equally stupid solution. So no, if there's bad data, now this stuff is obviously bad. There's going to be a lot more subtle cases where it's not, and those are the cases that Chuck mentioned as big challenges. There may be other bad data in here that I did not recognize. Matter of fact, there probably is. And if somebody can find it, then you know they might get a free Allsup's burrito from me next time they're down in West Texas. Okay, I'll scatter shoot across a few more potential model analysis pitfalls. Somebody tell me what's wrong with this analysis. Actually, I'm looking at this analysis. I'm seeing at least 4 things wrong with it that have to deal with the same theme. What's wrong with this? These are isodrosotherms. These are isotherms in Fahrenheit. What's wrong with that?
Isotropotherm higher than the temperature.
You got it. You would not believe how many times, even at SPC, but if I go into a forecast office while I'm chasing, or if I just watch people analyze maps anywhere, how many times that I will see isodrositherms cross isotherms and create a supersaturated atmosphere over huge areas. It seems really dumb, but people, a lot of times, they're so intent on analyzing a particular field that they're not paying attention to, is it reasonable given the physics of the atmosphere. In this particular case, 50 degree, there's a crossover right here, there's one in here, there's one over here, there's one up further north, where the, or actually in there, where the isodrositherm crosses the isotherm, creates a supersaturated air mass. Like I said, this seems really simple, but you'd be surprised how many people do stuff like this on maps. It's amazing. It's also wrong. Now, I could get into the evils of relying on objective analyses, and they probably run me out of here for using excessive obscenity. But let me use a map that I pulled off of a website, objectively analyze temperatures and dew points, and I apologize, it's kind of hard to read because my printer was not great quality this day, but that is an 80 degree isotherm, 75, 70, 85, 90. Now, what are some of the things that are wrong with that isothermal analysis? Well, I think most of y'all can see that this thing is analyzing on the wrong side of the data in a lot of cases. Now, in this particular case, I did go back and look at a couple of the surface maps, and it's like, well, you know, most of this data did seem reasonable. I didn't have the sounding data to look at, but I did go back and look at the surface maps. But the objective analysis scheme oversmoothed, and there is a tendency for manual analysis schemes to oversmooth as well. If you've got 5 minutes to prepare your zone forecast or your maps, and you're just scratching real quick, and you're trying to analyze, and you're drawing on the wrong side of the data, then you're basically drawing a lie, because what you're drawing is not really what's going on. Now here, for example, you have an 85 sitting north of an 80 isotherm, and 89 sitting on the 80 isotherm. Obviously, there's a problem there. And let me move it up a little bit to the dew points. You can see some similar problems with this. 65, there's a 57 south of the 60, on the wrong side of the 60. There's several others. There's a 72 on the wrong side of the 70. And again, the objective analysis oversmoothed for this. People do that with their hands all the time. Al mentioned a forecaster who was using model analyses of the data. The data was wrong. I've seen forecasters sit there and plot up objective analysis on Mercatus or on GemPuke, and what they end up with is they're relying on data that's bad. They're living a lie. The data is wrong. So why even bother? Draw the data manually yourself. If you don't have time to do it, make time to do it. Don't sit there and chat about how bad the Cowboys are. I would rather you not do that anyway. Instead, analyze maps. Now, on that particular website, which will go unnamed for their protection, they're explaining, okay, sometimes the reported values are not always located between the and they go into all this hand-waving as to why, oh, the data is really dense, and if you tried to draw for the data, it wouldn't be able to it wouldn't be readable to the readers. So in order to make it readable, we're going to make it wrong. Now, you tell me how sensible that approach is. What I suggest is make the correct data readable. But obviously they don't see it that way. There's another case there with the dew points. They actually put more data on there, and you can see there's more data on the wrong side of the lines. But I hope you learn from this that if you rely on objective analysis, you'll get what you deserve, garbage in and garbage out. Okay, here's a case of objectively analyzed isobars, and I have to laugh because this sucks. But you can see what's going on here. Actually, most of these lines are close to the right place on the data. It's kind of hard to tell because the plot is so big, it makes it, you're not sure whether it's on the right side or not. But look at this. How many fields in the real atmosphere have you ever seen that have these zigzag straight lines? It looks like the dot to dot in your local Sunday paper, the comics page that kids do. I've seen people analyze maps like this too. And okay, you have a trough here, a trough here, a trough here, a trough here. Oh, look, there's another trough here. That one may be real. A trough there, a trough. Look at these, a veritable plethora of troughs. Something big time is going on in the weather. Now, but I hope you see what I'm trying to point out here. Objective analyses and actually paying attention to your own manual analyses. Okay. I'll switch a little bit in mode to soundings. You're analyzing soundings. Obviously, most of you are using software packages like Sharp and sounding analysis packages in Macitus or Weather Graphics or GMPuke or something like that. For example, here is a Tallahassee. This is actually a forecast sounding, but the same principle applies if you use an observed sounding. It matters how you analyze soundings. It matters what parcel you use to lift. Here's a case where you have a shallow moist layer right in here. You're mixing out through a fairly deep layer. And chances are, this, as you continue to mix, this is going to dry out some if you're getting insolation near that site. What I'm using here is the most unstable possible surface parcel, the worst case scenario to compute CAPE and to find the maximum parcel level. In this particular case, this is probably an over forecast. It gives you the worst case scenario, but I would argue that a more reasonable analysis would take into account the mixing away of that moisture. And here's a case where we did mixing. Now the software package didn't allow me to customize the mixing layer. I'd made it different, but it mixes using the mixing layer, I believe the lowest 100 millibars, and you end up with a dramatically different CAPE. As you can see, that's 163 joules per kilogram. That storm may not even form in an environment like that without serious help, versus 2,274 joules per kilogram. This particular sounding package uses the virtual temperature correction that Chuck and Eric have written about, and I have a link to that in some of the publications on the SPC homepage if you're not familiar with that paper. But some sounding analysis packages don't. Some sounding analysis packages use a surface-based parcel. Some use some depth of mix layer. Some use something I don't know what it is because I can't figure it out. Weather Graphics might use something different than Macitus, might use something different than the SPC analysis package. Know what it's using and know how it computes the parcel, and even more importantly, what is appropriate for the particular situation. In this, like I said, lifting a parcel using a mixed parcel is probably a little bit more representative than the most unstable possible surface parcel. There's other cases where you may have some convection that is rooted up above a relatively stable boundary layer. The sounding is cold down low. Let's say the sounding goes up through a front into more unstable air. Well, you might be able to use the most unstable parcel from the top of that frontal layer. If you try to use the soundings automatically computed mean mixed parcel, you're going to end up with an unreasonably stable sounding, no instability, or no CAPE. So that's a little bit of an overview on pitfalls of analysis, severe storms forecasting there. Now I'm going to go a little bit into handicaps using numerical guidance. A lot of the times it's in the forecaster using it. The model never thinks that it's wrong. The model's an inanimate object. But it has its problems, whatever model you're using. Well, how do you find out what's wrong with the models? Well, and what's right? Well, there are some published overviews of each. Some of them may be outdated. I know Fred Carr down at the University of Oklahoma regularly updates his little journal on his little book on what the characteristics of the models are, and it's good to learn. You really should learn the basics of of the model physics to the extent that you can. There are bulletins on model adjustments that are issued by INSEP. They're irregular, they're sometimes obscure. They might quietly issue them and not tell anybody. And they may not even know what's wrong because it hadn't been operationally tested for long enough to find out for sure. You can read SPC discussions. Well, you can't go wrong, of course, there. But you can read SPC discussions, INSEP, WFO forecast discussions. Like I say, they're a great short fuse resource, but care must be taken because what if the forecaster is not interpreting it right? Well, you still don't know. You can depend on word of mouth, your family and friends. Good luck. The best one, experience. As you forecast, analyze, analyze, analyze. You're looking at the models. Over a period of time, you'll not only see biases in observed data like I showed you before, but you'll run into model biases. INSEP may not even know about them. We've discovered a number of biases with features that are important for severe weather forecasting that INSEP didn't even know about, and we discovered them operationally. I'll show you a couple of examples later, but that was gained through experience. You actually have to do the work yourself. Here's an example of what I was talking about, for example, with the using discussions. Maybe you can read a discussion, they'll point out a feature that you were not aware of before. For example, northern Mexico Rayab data void. The trough was poorly depicted because there was no Rayab data over northern Mexico. Well, how do you know it's really even there? Well, that's a good question. Maybe a forecast discussion such as this could help you think about that a little bit when you're trying to forecast severe weather downstream later during the day, and you can look at other data sources to see if it was really there. As I said, though, some discussions may be erroneous interpretations. The INSEP issues a technical implementation message called a TIM. It comes out on the Noose 41 WMO header every once in a while, and sometimes it will actually be relevant. And in this particular case, they're talking about global model runs, changes that are going to be implemented in the spectral model, in the American spectral model. And of course, famous last words, a forecaster will see little difference. When you see that, shake your head and say, ah! Because chances are there's going to be something go seriously wrong and you're going to end up with a bad forecast. But in all seriousness, every once in a while these can tell you, they'll be embedded within these things, something important about changes that have been made to a model that could influence the forecasting you're trying to do. Severe weather, lake effect snows, whatever. For example, let's say there's been a change made to the soil moisture parameterization. Well, as Rich talked about before, that can influence severe storms. I mean, if the model couldn't handle soil moisture worth a hoot, how could it forecast an event or the environment favorable for the plain field tornado in the boundary layer, for example? So things that seem obscure may actually be important. Here's a case where if you spend all your time looking at derived fields and not some of the basic parameters such as temperature and dew point, then you would have gone wrong. Back in, so I believe it was 94 or 96, this problem was very, very apparent to a lot of people. This is an ETA model forecast, 48-hour lifted index forecast. I could have put a CAPE forecast up here if I could have gone back and found one. It would have yielded a very similar profile because I remember that happening during that particular summer. It did that a lot. Well, look at what the situation. We had a surface low out here somewhere. We had a dry line, warm front, strong lifted indices, or small lifted indices values, negative lifted indices along the warm front, and it looks like all hell is going to break loose near that warm front. Nothing at all is going to happen down along the dry line. It's too stable. 4 LIs. Oh, well, the model must be right. It's the model. It can integrate equations better than I can, so it must be right. Well, this is the verifying analysis. This is actually the initial model analysis, which may not itself be entirely correct. It's not a plot of lifted indices from the RAOB data. But you can see there's quite a bit of difference. I mean, there's -6, -8, -6, up and down ahead of that dry line. And then back around the north side of the surface low, there's some instability. Look at the difference there. I mean, the model really just screwed the pooch big time on these instability forecasts. -6, -8, look at this. Over South Texas, a -6 LI where it had around 1 to 3 degrees positive lifted indices. But yet, if all you ever look at is a derived field, if you're making a forecast for the day, you're kind of in a hurry. Oh, we're not going to have anything today. The lifted index is positive. Well, then you deserve what's coming to you because your forecast is going to go down the toilet. I'm going to go into a little bit of a case here. You can see the overall pattern. The 24-hour NGM forecast, and a lot of you realize the problem with NGM instability forecasting has showed up for a long time, and I'll give you a case of that. There is a shortwave trough at 500 millibars moving across the mid and lower Mississippi Valley. There's the model is predicting that this particular vorticity, zone of strong vorticity, is going to move across in this area. And associated with that, not shown due to time constraints, was quite a bit of cold air in the mid-levels. There's the 24-hour forecast of the NGM lifted index. So you think, okay, well, that corresponds pretty well with the Vort max of -5 LI. Well, the model must be right. It makes all the sense in the world, don't it? Well, you're not thinking about it deeply enough, because what in the world would cause something like that to happen? Well, maybe it's right, maybe it's not. We'll just have to see. Well, there was the verifying ETA analysis, 500 millibar height and vorticity at the time. You can actually see that the NGM, the no good model, actually, it's kind of hard to tell on the overlay there. I'll put them top to bottom. Get them straightened out here. The ETA verifying analysis is on top. The NGM forecast is on the bottom. The NGM did forecast a little bit different orientation. The strength is roughly the same. And so you say, well, that's not that bad of a forecast, at least in that area. Upstream is a different story. Well, maybe you're not suspicious enough of that NGM lifted index. There's the verifying analysis, ETA surface model pressure, wind, thickness. In the actual surface data, I was not able to go back and get for this case, unfortunately, but it has a low over southeast Kentucky, northeast Tennessee, and the forecast, the large negative lifted indices were back here west, over or just northwest of the surface cold front, back in this area. Hey, there was a verifying analysis for the NGM-LI. You see there's nowhere near the kind of bullseye there was before over that area. And I'll go back and pull up the NGM-LI forecast so that you can see for yourself. There's the forecast over the same area. -5 and -3. Now there's still a little bit of a maximum in there. The verifying analysis, the ETA model lifted index, barely any negative LI at all, 0 to -1, whereas the NGM forecast had a -5. I was able to go back and look at the sounding. And then just for comparison, there's a verifying analysis of the CAPE computed from the ETA, which there are problems with that too, obviously. If the ETA model computes CAPE using a surface-based layer, then it's not going to pick up on CAPE that's elevated, such as what was probably going on up here. But That's what the CAPE analysis looked like, and you see there was some convective inhibition plotted north of that. It did indicate some CAPE up there that was under the contouring threshold. Well, you're still wondering what's wrong with that. Well, looking at the NGM 24-hour forecast sounding, this is not as extreme as some cases I've seen, but you got parcel that's nearly saturated through this layer in here, and as a result of a lift in the parcel from the surface, you end up with a pretty large lifted index of 500 millibars. Well, I've seen some soundings for NGMLIs where it has almost a dry adiabatic lapse rate with a completely saturated layer. Well, that makes a lot of sense, don't it? Get away, bug. If there's anybody out there that's an animal lover, then you can leave now. There was an EDA model 24-hour forecast sounding for that case. The lifted index looked a little bit more reasonable, so did the lapse rates, especially given that it was a nearly saturated environment. There is the closest sounding that I could find, and I modified it for some surface observations in the area and some interpolations of RAOB data. So it's not exactly the Birmingham sounding. I'll just do a straight overlay here after I show the sounding itself. Well, okay, there's even a problem with this observed sounding. Can anybody tell me what it is? Hmm? Mm-hmm. And why is that?
When you come out of the cloud.
Mm-hmm. That's actually a very common problem. The way the sensors are, you get these false pseudo-adiabatic layers lifting up out of the top of cloud layers, and ends up giving you, in this case, an instability that doesn't even exist. Chances are the profile looked more like this. There's a lot smaller LI and a lot smaller CAPE. So actually, fortuitously, it may even have had it right for the wrong reasons. The EDA model had a better LI than the observed sounding did. You won't see this happen too often. You can also see there are some other fairly significant differences between the EDA model forecast and the observed sounding. That's why I say it had it right for the wrong reasons. The EDA model forecast had it much cooler in both temperature and dew point throughout that whole layer than the observed sounding did. A little bit better in the upper levels, but not much. The photographs are all over the place. It just goes to show you can't depend entirely on the model data because the observed data might be different, and sometimes the observed data may be wrong. So you got a lot to think about there. In case you're wondering what actually happened that day, if you had forecasted a lot of severe weather, a lot of hail, or near where that lifted index maximum was well inland, well back over the cold air, you would have busted the forecast because nothing happened. All the watches and some severe weather were much further south and southeast. Now the NGM, unlike the EDA model, is static. It's stuck where it's at, and it'll probably remain so for the rest of its life. It's being used for MOS. And so the equations are being left as they are. But I will give you some severe weather-related NGM biases because unlike the EDA model and some of the others, it's not being changed all the time. The biases change as the model physics are messed around with. Some of you realize lows coming out of the Rockies too far north and too intense. This is a long-term problem. I was just talking with Steve Silverberg about that a little while ago. That actually has not been as much of a problem this year, but in previous years it has been. Not because of any change in the model atmosphere, but because of a change in the real atmosphere, as it turns out. Poor skill in cases of extreme instability. Low probability detection, high false alarm rate, as you saw, and that was not an extreme case. There are other cases where it had, NGM came up with -8, -10 LIs with a dry adiabatic lapse rate through 400 millibars of almost 100% relative humidity. And excessive moistening and warming of the lowest layers, excessive cooling of the middle levels to near saturation, which is one thing we saw there. It has had a pronounced warm season tendency to overdry the low levels, even with southerly flow under the capping. It tends to mix out for whatever reason. And I'm not sure exactly why. Over drying, though, if you dry out the low levels too much, if you dry out the surface, that leads to overheating, leads to a little bit too much vertical mixing. Sometimes bogus inverted V sounding profiles, you compare them to the real sound and it's not there. Not enough convective inhibition results from profiles like that. Obviously, if you destroy the, if you create a false inverted V profile and destroy the cap, then it's forecasting convection where there is none. And it has tended to under-forecast CAPE in extreme CAPE cases. Now in the cool season, NGM has had a noticeable dry bias with Gulf boundary layer return flow, some of the things that Rich was talking about. Steve Weiss of Cells did an exhaustive look at this during the GulfMex project and found that the NGM was not forecasting the return flow to be of the magnitude or the duration that it was, or the moisture, the higher moisture values to come back as soon as they did, even though the patterns looked fine. The low-level jet was about in the right place. The shape of the moisture pattern was good, but the absolute values were not. And another thing that Steve found was that deficiencies in the NGM boundary layer physics and convective parameterization really contributed heavily to LI and CAPE errors. So it's not just a problem of saturating the mid-levels too much. So also related to what Rich was talking about, some model problems that the ETA has had. Now it, again, has been changed quite a bit this year, improvement in horizontal resolution, which I can go on a tirade about too, but ETA model moisture return during a cool season, it has had a tendency to return moisture inland too rapidly during the cool season. Now since we've gone to higher resolution over the last couple of months, I really haven't had enough cases to look at and say it's still continuing. But before then, it's tended to actually return the moisture too fast. It over-forecasts low level moisture not only just in the initial phase of return flow, but as it continues well inland. Dew point's too high for a long period too far inland. Along the north and northeast edge of the moisture gradient, and in most of the 24-hour forecasts, I tell you, you just can't win for losing, can you? That's right. Anyway, and even in the 48-hour forecast, it was actually the maximum errors showed up in more of the 24-hour forecast than they did in the 48-hour forecast. Something's wrong with that picture. You figure the models would get better as you get closer to the event. That's not necessarily the case. The lesson to this is, through experience, through reading whatever documentation you can get a hold of on the models, know their biases and be able to apply their biases to the extent that you use the models in your forecast. So if you just blindly pull out a model and look at it and make your forecast off of it and you're wrong, then I have no pity on you. Here's an example of the moisture return errors along the Gulf Coast. And I'll fast forward here a little bit to the 48-hour forecast error compared to the actual forecast. In this particular case, the ETA model showed tremendous errors right along the central Gulf Coast here with forecasting the dew points. Now, again, I'm not sure what the tendencies are. Rich might be able to elaborate a little bit more because he's actually seen a few more of these on duty than I have the last 2 or 3 weeks. Ignore this type A, B, C error stuff. What we're really looking at here is ETA model forecast errors along the Gulf Coast with moisture return, the 24-hour ETA model forecast, verifying analysis, and the forecast error. And again, there's a considerable error in the dew point forecast along the Gulf Coast. So if you're only using models to forecast return flow, you can have problems. You go into the equilibrium dew point techniques that Rich outlined, you'll be able to do a little bit better job. Okay, ETA model, the spectral models are changing all the time. What do? Can you cope? Well, I should hope you can. Realize that the primary inset models are being updated often. They are. a bias that you see over a period of 3 or 4 or 5 forecasts this year may not show up next year. If you keep abreast of what's being changed in the models and you find something that may influence your forecast, watch for it. Like I said about the soil moisture, maybe that will influence it. Because of that, forecasters can't depend on the persistence of the biases, except in the frozen NGM and the NGM moss. But it's becoming more apparent to me, NGM to me, to a large extent, is practically useless for forecasting severe storms for a number of reasons. But at least we know why. And we know that it's going to stay equally useless most of the time under similar situations because we know what its biases are. Many performance characteristics of the models can change fast. When tinkering is done, so-called upgrades to model physics, forecasters should notice a little difference. Sure. Like that, what I showed you with the 1996 mixing errors. Somebody tweaked some soil moisture and radiative parameterization a little bit, and all of a sudden, the model went to hell for forecasted warm sector instability. We didn't know it was going to do that. INCEP didn't know it was going to do that. I mean, we were innocently ignorant at the time until we actually saw these things showing up and brought them to their attention. And obviously, something like that can not only influence severe convection, it can influence forecasting snows, heavy snows, it can influence forecasting QPF, precip forecasting. And there's a lot that's going on in the models that you may not be aware of. INCEP, like I said, they do run tests, some tests prior to implementation of the changes to make sure that there's no obvious problems. Well, in one case, there were no obvious problems during the cool season, but when the warm season hit, the temperatures at the surface were 10, 20, 30 degrees Fahrenheit off, the dew points were almost as far off, and the forecast was awful. The tests don't run long enough to be able to find all the problems that can crop up in innocent changes like that. Forecasters must know when major upgrades occur, and obviously, like I said, after the model tinkering, pay close attention to the parameters important to your type of forecast. And like I said, even minor, seemingly trivial stuff, soil moisture fluxes, radiation balances, maybe they've switched convective parameterization schemes. Actually, that's not minor, but something like that can have a huge influence on your forecast. Surface dew point, surface-based CAPE, for example. Big differences as I showed you. I like to look at model forecast soundings at work. And it's a very useful tool for trying to judge what the models will do. The models are trying to do with the atmosphere, not just at one level, but through the atmosphere, and look at time sections of model forecast soundings. For those of you familiar with BuffKit is a Weather Service software package that animates forecast soundings. So you can see through a period of time at least what the model is trying to do with the atmosphere. You've already looked at the real soundings, you've done your own analyses. Well, it's up to you. Forecast soundings are really great, but if you're not interpreting them right, they can go crazy. Now this right here is your typical weather forecaster type, and you know, he's got a dilemma here. You know, on one hand, the little demon's telling him, "Oh, your problems are solved. Look at model forecast soundings. You're looking at this wonderful atmosphere here. It's going to go great. You can't lose." And of course, his conscience is telling him here, you know, they can mislead you. You have to be aware of the model biases. You have to analyze. You have to know what the data. Don't ignore contradictory observations. A lot of forecasters look like that, don't you agree? I'll throw one case up here. Here's an analysis done off of 0Z to 12-hour sea level thickness and pressure. And we're talking about forecast soundings here, so keep in mind where these features are. I went back and unfortunately the surface data I couldn't get to plot up well, so I just used the model thing, and that's why the front doesn't agree exactly with the model initial analysis, because I was looking on screen at the surface data at the same time. Unfortunately I couldn't get it to print out. But there's a low, surface low, pretty close to Tallahassee, between Tallahassee and Appalachia, trough which was kind of hard to see in the real data because there's only a couple of data points out here, extending southward from that and the front down into the Bay of Campeche. We're going to look at a forecast sounding for Key West. This is out where we're getting a lot of warm, moist trajectories from the Atlantic. The air mass is long since been modified as it's gone for over 1,000 miles across the Atlantic. It's almost a subtropical warm sector at the time. 500 millibar initial ETA model analysis, there's Key West. There's some weak trough out over the eastern Gulf. Examination of RAOB data, what little I could, and continuity back over Mexico, where there actually was some Mexican RAOB data from the day before that, made me agree that yes, indeed, there's a trough there. Higher up in the atmosphere, water vapor image indicated that. So I had reason to believe that the trough was good, even though, whether it was that strong or not couldn't find out for sure. And look at Key West again here. Actually, I think I got that backwards. That should have been before that, but you can see Key West is in the moist sector, in the warm sector. They got east-southeasterly flow off a broad fetch of the subtropical Atlantic east of them. And trough is forecast to move past Key West to the north. Keep that in mind when you look at these forecast soundings. Here's an ETA model forecast sounding for Key West at 12Z. Forecast soundings are the way to go, right? There's the NGM forecast sounding for Key West at 12Z. A little bit of a difference, right? 2,000 Cape, 598 Cape. The soundings look quite a bit different, actually. I'm lifting them the same way, so there's no difference in the parcel I'm using. But yet, there's a huge difference in the amount of Cape. Lapse rates are very similar, but the main difference is that is way down low. The ETA model is actually warmer, and so it gives you a little more instability. Just for fun, aviation forecast sounding, which actually ended up closest to the correct Cape, but the vertical resolution of the aviation model leaves something to be desired. You can see we're not going to get the greatest photographs in the world from something like that. And the Cape ended up being fairly close to that, as I'll show you on the forecast sounding, but I think the aviation in a lot of ways was right for the wrong reasons. There's the observed sounding. Ended up with a Cape of 1541 joules per kilogram, which is as close as any of them to 1320. And I'll actually overlay them so that you can see. Okay, it did pretty well thermodynamically, but how about kinematically? Well, it stunk. The AVN hodograph yielded storm relative helicity of 49 compared to 176 for the observed sounding. So if a storm had gone up in that environment and you relied on this particular model forecast, you would say, supercell's not likely. If a storm goes up in this environment, there's a little bit better chance. Well, this was as representative as that sounding can be of the environment close to where it was. And there were big differences between the model forecast and the observed Capes. There's the ETA model, there's the observed sounding. I'll get these as close together as possible here. And you can see that it looks like it's only a couple of degrees at any particular level, but integrated through a deep layer, you end up with a much different Cape. So forecast soundings are not to be used literally. Here's a forecast from the 0Z to the 12-hour precip forecast, and there's actually a forecast of a lot of precipitation well west of Key West. Key West is out here in the moist sector, in the warm sector. There's very little lift going on in that area. No storms actually went up there. Now, you believe the NGM forecast, then Key West was getting bombed. Strong kinematic vertical velocities. Precip fields are very strong, but as it turns out, no thunderstorms moved over Key West. Let me get that NGM forecast sounding back up here. And see some effects of that precip forecast in the NGM, and that its environmental lapse rate is moist adiabatic the whole way up, because the NGM is basically launching up through a model thunderstorm or model convection that does not exist. Okay, we'll look at a ETA model forecast sounding for Jacksonville. How many of you have ever seen a sounding in the real atmosphere that looked like this? Maybe some soundings in tropical cyclone environments where it's a little bit warmer near the surface and you've got deep, near saturated layer all the way up. Strong vertical shear is evident in the hodographs. The 3075 storm motion would have been somewhere about in there. And storm relative helicity is computed of 274. Now that was the model forecast. The model forecast obviously stunt, especially with regard to mid-level relative humidity. This is what it actually looked like. Let me get it overlaid a little bit better. Now what do you think the model was doing that would cause that kind of difference, especially in there? Any ideas? Why would there be that deep, high relative humidity layer all the way up to the tropopause and into the stratosphere? Well, I'll show you what the model was doing. It had Jacksonville under this tremendous vertical motion and precipitation bullseye. It had cooled a large section of the atmosphere to near saturation. It had too much moisture everywhere. And what you ended up with was a precip forecast. What actually happened, the line of storms at the time was west of them. The model was actually much further west than that, back in here. The model had forecasted it to already start there by then. The forecast didn't verify. So there's a few pitfalls of using forecast soundings. Now, I'm going to go into one of Chuck's favorite topics here. Those of you that have read his homepage, you can just, thoroughly, you can probably leave right now. But it is a common error for forecasters to make on the fly, to see strong areas of PVA at 500 millibars and say, oh, look at the lift going on here. Look at this lift. Look at this. It's a trigger. And of course, you know, somebody like Chuck would be back there having a coronary, but for good reason. I'll show you a case, an actual case where this don't work. But I'll briefly go through this. Those of you who haven't seen this will before long. By the way, if you have not been introduced to this yet, this is what you're going to see here in the next couple of years of your undergraduate studies, so prepare yourself. Quasi-geostrophic height tendency equation. Basically, what this thing is telling you, if you're not familiar with the math yet, is that net downward vertical motion results, not height tendency, but the vertical motion equation here. Net downward vertical motion results in weak DPVA and very strong cold air advection. DPVA is differential vorticity advection. I just use positive here, but it could be negative as well. It's just the difference. Net upward vertical motion results in weak DNVA and blister and warm air advection. Well, you're considering, when you talk about PVA equals dynamics, you're only considering this. You're not considering this. And in many cases, the warm air advection or the cold air advection completely overwhelms that term, might completely overwhelm this term right here, and you end up with completely different atmosphere than what you think you've got. Okay, let's look at let's look here off the coast of California. It's a no gaps forecast. Relative vorticity, didn't have absolute. Relative vorticity, 500 millibar heights and 12-hour height changes. Now, this is implying that there is negative vorticity advection near the California coast through this area right here. Now, if you just looked at that panel and read a forecast discussion somewhere, you might see, oh, NVA over the area, we're under a ridge, nothing much is going to happen. The lazy forecast approach. Maybe a little bit hard to see the coastline here, but I'm actually going to show vorticity advection at 1,700 millibars, and vorticity advection is becoming negative with height in this area. And it's kind of hard to see, but there's the California coast. Not much is going to happen, right? Well, here is a no-gaps analysis, 1,500 millibar thickness, 700 millibar vertical motion. Well, uh-oh, wait a minute. Where's it getting that vertical motion from? Isn't there NVA there? Well, wait a minute. Something's wrong with this picture. You didn't consider thermal advection. Where's it getting all this precip? Lots of precipitation along the California coast. Wait a minute, we're under a middle and upper level ridge. There's NVA. Nothing's going to happen. Well, this was the difference. There was actually quite a bit of warm advection over this area, a lot of precipitation, and it was not just orographically forced. In the model, remember, there was also precipitation offshore, and if you can convince me that the precipitation offshore is orographically forced, well, then I'm just going to quit the business. So that's just a little bit of an illustration of the fallacy of just taking some simple rule of thumb, and instead of actually thinking about how the atmosphere really works, at least in the quasi-geostrophic sense, oversimplifying things. Oh, PVA, lift, trigger, convection, ready-made, instant mix oatmeal, we're going to have thunderstorms. It may not work out that way. Well, I kind of scattershot through some of that stuff, but I hope you learned some lessons about what kind of things to avoid in forecasting. I'm going to flip this off because it's hurting my eyes. And I will open the floor to questions about that stuff or about SPC in general or whatever I can answer. Yes?
FSL seems to be really talking about the RUC 2 model. Is that quite an improvement that you know, or have you played with the RUC?
Played with the RUC 2 model a little bit. Not enough to say that it does better or worse in severe weather situations, because I've only worked a few cases where I've seen RUC 2 output, and in those cases it and the ETA model perform fairly well with most of the temperature and low-level parameters, and I haven't, like I said, I haven't noticed enough cases to really say for sure that it stinks or that it's great yet.
So far this month, the RUC 2 errors at 12 hours and the Meso ETA model errors at 12 hours are about the same.
Okay, well that would jive with what I've seen so far, but like I said, there hadn't been a lot of cases.
By the way, I just want to point out, NIU has been doing a model verification where they're looking at some of the model biases on that, and I guess you're going to be putting in a new 0-hour analysis verification with an actual observation. Do you want to just make mention of that?
Well, we won't be able to do that. What we're planning to do is to actually this week, now that spring break, we can actually breathe. We're going to actually just look at comparisons, inter-comparisons between different model and visual analysis. So, for example, we'll take a look at ETA model analysis of mean sea level pressure compared to engineer mean sea level pressure analysis, compared to aviation model mean sea level pressure analysis, the RUC model mean sea level pressure analysis. We look at 5 millbar height fields, relative humidity fields, wind speed fields.
For those of you who have not seen his model verification page, visit it. It'll really open your eyes up in a lot of ways. You can see some of these biases, for example, in return flow unfolding, or in some of the biases with the NGM with lows too far north. Like I said, not so much this year, but in previous years.
You know, I think it underscores what we started with Chuck this morning and ending with Roger here is there's a tendency for forecasters to rely on the models. That's what they look at first, that's what they look at last, that's what they look at all in between. When the model screws up, if you don't know how to analyze and determine why the models are screwing up, you're screwed up, so to speak.
Yeah. You can have the best analysis in the world. The model can still be wrong, and if you don't know why it's wrong, like, for example, in the case of that precipitation bomb around Jacksonville, if you didn't know that the model was forecasting a huge blob of convective precip there, nearly saturated profile through a deep layer, you almost never see a sounding that looks like that, then you might be just lost.
Yeah, I've noticed in looking at a lot of forecasters' analysis work, they often will do isotherms, isogosotherms, pressure analysis, and they'll put in the most important boundaries, but they'll leave a lot of more subtle boundaries out. They won't even try to analyze that there's a boundary there. Furthermore, I often get briefed, and somebody told me something like, well, this front is washing out today. It's going bye-bye. Well, a large area of thunderstorms develops on it, and I come in the next day and I get the same thing. Well, that old front's still washing out. And then there's another large area of thunderstorms along, and day 3 I'll come in, and it's the same story. Boundaries are one of the most important things you're looking for when you're looking for convective forecasting. And you've got to be able to analyze even the most subtle boundaries, so you've got to do a very careful analysis. And don't stop when you do the isotherms and isogosotherms and pressure analysis. That's when you're reaching the point that you can start to pinpoint the boundaries.
That's right.
Satellite data and hazard analyses and everything else.
And that's where that's...
Trying to prematurely wash those systems out.
That's where that supplemental data I mentioned comes in handy. VAD winds, profiler data, might detect features in levels in between the mandatory levels that you don't see in your RAOB analyses. Supplemental surface data. Mesonetwork data. Maybe if you're analyzing a map over Oklahoma, there's some weak, long age boundary that's still in there that's very subtle. You don't see it in, say, an analysis. You see a very loose temperature gradient, for example, between Oklahoma City and Lawton, but in the Mesonet data, that almost the same gradient is actually over one county. The boundary's really there. So Al's raising an excellent point. You don't assume a boundary is dead just because you don't at first glance see it on the map. Look for clues to it. If it's been there before and you haven't had something obviously to remove it, look for it. It might still be around.
Roger, a good example of that is June 15th of 92, the Central Kansas HP supercells, whatever, all sorts of tornadoes. There was a subtle boundary east-west across the Kansas just around the interstate, I think. And I did see one study, and the HP supercell studies show that these usually occur along boundaries. And they said in this case there was no boundary. And right in front of them there's data that says there is an important boundary. It's just that it was highly modified on the north side with high dew points and only somewhat cooler temperatures than to the south. But it's where everything fired up. It was a big time there. It was the biggest days in Kansas in a long time.
Oh yeah. Well, I'll tell y'all another little clue for locating returning fronts in keeping with the theme that Rich did. Let's say you've had air mass out over the Gulf for a long period of time. Several days ago, the front passed off the Atlantic coast, and you're not sure exactly where, for example, the strongest isothermal gradient might be out over the Gulf of Mexico. You've got some trajectories from the Caribbean, but you're not sure where the leading edge of them is. Well, you can go back over a period of 3 or 4 days, look at satellite loops or still satellite pictures if you don't have loops that go back that far, Watch that trail of low clouds across the Atlantic, curving back over the Caribbean and into the Gulf of Mexico. There might be a few gaps in it. Maybe you can connect the two, but if you don't have the data, that might hint as to where the leading edge of the maritime tropical air mass is, and then you can go look at your sea surface temperatures, look at your trajectories, and say, okay, I don't know for sure that it's there because I don't have the data. I suspect it might be there, and I'm going to be on the lookout for it. That's another example. Supplemental data.
Roger, you bring up another point that's really interesting, and that is that as a human being, you can integrate data, information that's not quantitative.
Mm-hmm.
You can look at the satellite image, you can look at a radar image and make reasonable inferences about what's going on without actual quantitative information. And numerical models and all of that, they depend on being able to deal with it quantitatively. And if they can't, then essentially they're in the dark. As a human being, you can integrate all sorts of information. And what I was talking about this morning about a conceptual model, matching it to data, you're trying to come up with a picture that's consistent with everything you've got, including non-quantitative information.
Most of the people I've seen who misanalyze features like boundaries don't have that conceptual model. They're just not thinking in terms of conceptual models. Mm-hmm. It's not a clear picture to them what they're looking at.
And if that conceptual model that you have is highly deficient, in other words, it's based purely on something like, 50-degree isotherm for the dry line, you're going to analyze the dry line all the way around that thing, and you end up with a bad analysis and a bad forecast.
Any other questions?
Yeah. For your model that you showed, what hour were those? Were they 12 hour or 24 hours?
Let's see, which ones are you talking about?
Like the Key West, Jacksonville?
Okay, let me go back to those. Okay, the ETA forecast sounding for Jacksonville was a 12-hour forecast. That was only a 12-hour forecast, and it was off by as much as you saw. I don't know if I can dig out the actual sounding again, but you remember there it is. It was a forecast for January 8th at 0Z. It was a 12-hour forecast. I have it written on the side, but not actually on here. And that much of a difference just in 12 hours. You'd think the model could do a better job than that, but it didn't.
Okay, just one last thing before the banquet. I'd like to ask all the speakers if they would all sit at the stage side of the table, maybe one per table, so this will be able to mix up as much